In an attempt to study how gases behave, an Irish chemist named Robert Boyle in the year 1662 came up with a law which we call the Boyle's law. It states that the volume of a fixed mass of gas is inversely proportional to its pressure, provided the temperature remains constant. So he found an inverse relationship between the volume of a gas and the pressure. In other words, increase the pressure, the volume decreases. Increase the volume, the pressure decreases. Volume V is inversely proportional to the pressure. Or we can say that V, if you have to remove the sign of proportionality, you introduce K. So we can say that V is K, that's the constant, over P. Then we can also write this when we make K the subject of the formula. That will be K equals PV. So there you have it on your screen right there. That's Boyle's law. So how do we apply that to solving some questions? On your screen here, the question you have here says a gas at a volume V naught in a container at pressure P naught is compressed to 1/5 of its volume. What will be its pressure if it maintains its original temperature? So what we have to do is to list out what we have first from the question. Okay, so we have the initial volume. That's a good place to start. That's V naught. We have the initial pressure. That's P naught. So then we have the final volume. According to the question, it says that the volume was compressed to 1/5. Okay, so we have a movement from V naught to 1/5 of V naught. So we can say now have 1/5 of the original volume. Then the final pressure, that's what we need to calculate. And from Boyle's law, we know that PV equals K. Okay, we'll have that from the pressure of a given mass of gas is inversely proportional to its volume, or the other way around. It's still the same thing. All right. Okay, so here in a case where we're comparing two pressures and two volumes, you have this formula will now become P1 V1 equals P2 V2. That's the first pressure multiplied by the first volume equals to the final pressure multiplied by the final volume. The final pressure, how about we make it the subject of formula, because that's what we need to calculate. So we have to make P2 the subject of formula. So how do we do that? So P2 will now be equal to P1 V1 divided by V2. So P1 is P naught. Okay, you have it from here. It's P naught. Then V1, that's the first volume, is also V naught. Okay, somewhere. Then V2, as I have it here, is 1/5 V naught. That's 1/5 V naught. Okay, then that would lead us into, so we can write this as P2 equals P naught V naught divided by 1/5 of V naught. P naught V naught multiplied by 5 over V naught. Okay, so let's just call out the repetitions. Okay, and we're left with 5P naught. So we can say that the final pressure is 5P naught. So that's our answer. So how do we apply the knowledge of Boyle's law to some of the case scenarios that you have on your screen right now? So let's say you have a cylindrical tube with gas trapped in it by a mercury thread. The tube, as I would like to point out, is of a uniform cross-sectional area. So I would say that when you check the size of these diagrams, they are not that equal, but that's the lapse in the drawing. But know that they are of uniform cross-sectional area, the 3. All right. P of the gas when the tube is faced upwards. Okay, now it's faced upwards. Up here, okay, is open, and underneath it is closed. So you have a closed end underneath it. So when it's lying face up, that's vertical, the gas pressure, which is P, will be equal to the sum of the atmospheric pressure. So the pressure up here is the atmospheric pressure plus now the pressure due to this mercury column, okay, that'll be X. Now if you look at the second case scenario here, where you have the tube inverted, okay, the closed end is at the top, okay, you have the atmospheric pressure here, and the gas is trapped by this mercury thread. So if you are to compute the pressure of the gas in this case, you will say the pressure of the gas is the difference between the atmospheric pressure and the pressure due to the mercury column. That's your X that you have there. That's X centimeters of mercury. So here we will have it in centimeters of mercury. Then the third case scenario you have here is when the tube is lying horizontally. Okay, your atmospheric pressure is here, X centimeters. That's the pressure due to the column of the mercury thread, and you have your gas right here. So if you want to compute the pressure of this, it will be the gas pressure be equal to the atmospheric pressure. And why is that? Is because the pressure due to this column of X is negligible. Remember that volume, okay, is length times area. So if we are to describe that with respect to gas, with respect to these diagrams you have, we would say that the volume is equal to the length of gas column. Now the length of gas column is what you have here as y2, and here y3 centimeters. So that will be y, okay, multiplied by the cross sectional area, that's A. Now remember that these three diagrams have uniform cross-sectional area. So let's go ahead and describe the pressure of the first case scenario when it is vertical. So when it is vertical, our volume will be y1A. Okay, when it is inverted, okay, our volume is y2A. All right, when it is horizontal, our volume is y3A. So I said earlier that the cross-sectional area is kind of the same, so we can leave out A. We can describe this for the vertical. We can say the volume is only equal to the length of the gas column, y1 centimeters cube. For this as well, we'll say y2 centimeters cube, and for this as well, we'll say the volume is y3 centimeters cube. In conclusion, we can apply the knowledge of Boyle's law to form a relationship to derive a general equation. Now, the relationship we want to form is between these three case scenarios that we have for the capillary tube. Okay, so what we know about Boyle's law is that P1 V1 equals P2 V2, and we can as well add one extra expression, which is when we are comparing three pressures. So we have three pressures, three different volumes. Oh, right. So the first pressure we have here is for the vertical. So we can have that as P plus X. Okay. And the first volume we have here for the vertical, you can see it here for the vertical, is Y1. So that's Y1. Now, P2, V2, that would refer to the inverted one. Okay, the inverted tube. So for the inverted tube, remember that we said the pressure is P minus X centimeters. Okay, that's the pressure of the inverted tube multiplied by the volume is Y2. centimeters. So we saw the pressure of the horizontal from what we have here is P, that's the atmospheric pressure, multiplied by the volume for the horizontal. You can see it from here, that's Y3. So the expression you have on your screen right now is the general equation. So here's a question for you. I'd like you to pause the video and try and solve it. Alright. A thread of mercury of length 12 centimeters is used to trap some air in a capillary tube with uniform cross-sectional area at closed at one end. With the tube vertical and the closed end at the bottom, the length of the trapped air is 25 centimeters. Calculate the length of the air column when the tube is held horizontally. B. Vertically with the closed end at the top. You have the three diagrams drawn for you here. Okay, so first things first, the vertical tube with the closed end at the bottom. What do we know about it? The first assumption we can make is that P, that's the atmospheric pressure. Okay, and the volume is the length. Okay, it's proportional to the length. So that's the two assumptions we can make. So from what we know concerning this particular case scenario is that the pressure of the gas is equal to the atmospheric pressure plus the length, that's your X. Okay, centimeters of mercury, that's 12. And this will give you 88 centimeters of mercury, as the case may be. Okay, so we'll have that as P1. So how about we get the volume of that first case scenario? Okay, let's just number it 1, 2, 3, so that you guys won't be confused. Okay, for 1, the volume, okay, we can just say that is V1. We're trying to build up the equation for Boyle's law. That's what we're trying to do. Okay, so V1, the length that we have here, that's 25 centimeters. That's the length of the gas column. That's 25 centimeters. Okay, now on the other hand, okay, for 2, since the question asked us to calculate the calculate the length of the air column when it is horizontal, so that's 2. So what do we know about 2? We know that when it is horizontal, to get our gas pressure is equal to the atmospheric pressure. So we can say P1 in this case is equal to 76 centimeters of mercury. Okay, and V1 from what we learned earlier, I have no idea of that. Okay, so this is P2, this is P2, then V2 from what we learned earlier. That's what we're trying to find out. So we have a case, okay, here, which we can connect with the Boyle's law, which is P1 V1 equals P2 V2. And when we make V2, that's what we're trying to find, the subject formula. V2 will be equal to P1 V1 over P2. And that will be 88 times 25 divided by 76. That's 28.95 centimeters. And the second case scenario is for us to calculate the length of the air column when our tube is held inverted with a closed end at the top. Okay, so here we'll have the first diagram. That's the vertical one. The volume is 25, we said that earlier. Then the gas pressure is the atmospheric pressure plus the length of that mercury column. That's 88 centimeters of mercury. Then we compare that against V. That's figure 3. That's why you have V3. That's what we're trying to find. Then the gas pressure for figure 3, you have that here is the difference between the atmospheric pressure and the length of the mercury column. That's X. So the atmospheric pressure is 76 minus 12. You have that there in your diagram. 12. That's 64. Okay, so you put that up against themselves. That's P1 V1 equals P3 V3. You make V3 the subject of formula, and P1 is 88 multiplied by V1, that's 25 divided by 64. That should give you 34.38 centimeters. So there you go. Thank you guys for watching.